Alrighty, predicting products. Couple of things to note. Like I said, you might want to have up your word equations PowerPoint, or just have up your polyatomics, your periodic table, the ones with the ions. Because you need to be able to label the oxidation numbers. You need to be able to know your diatomics. And when you're writing an ionic compound, remember the cation's always written first. We figure out the charges and make it add up to 0. Do not just transfer the subscripts when you write your product, because when you're writing an ionic compound, it's not based off of the original subscripts, it's based off of the charges adding up to 0. Now, if you're using the Google Slides or Docs, control comma is for subscripts, control period is for superscripts. That'll just make it go faster and easier for you if you're going to use the Google Slides for this particular lesson. If you're writing on paper, great, just follow along. All right, so up here, the synthesis reactions and the ones that we're going to do, very basic, really is one element, like element A up there, reacts with element B, and that's going to produce compound AB. So you're basically just taking the two elements and combining them, all right, into a single new substance. So for example here, we have potassium plus bromine. So you look at that and you go, well, potassium happens to be a metal. It's in group 1, it's an alkali metal. Bromine, halogen. Remember, bromine is one of those diatomic ones, so in elemental form it's a 2. These two combined together, the metal plus the nonmetal, what type of compound is it going to form? All right, we have the covalent acids and ionic. We have those choices. Which one is it going to form as a compound with these two beginning elements? Metal plus a nonmetal. No, what did you say first? Ionic. Very good. Metal plus nonmetal is always ionic. So in order to figure out the product here, we need to know the charges. So we have K, we have Br. Our two elements, if it's going to be forming metal plus nonmetal, we know it's an ionic compound. Let's look up their charges. What is the charge on potassium? Based off of the group that it's in. What is potassium's charge? Always. Off of our lovely periodic table. Potassium's not one of those moms or anything. It is +1. Very good. And bromine, when it's in a compound like that, where it's acting as an anion, meaning it gains electrons. Bromine being in a halogen, what is its oxidation number or charge going to be? Halogens are going to be what? What's their charge? -1, thank you. So when these two combined, it's a 1-to-1, +1, -1. So this is just going to form KBr, like so. Now I realize now it's really hard to balance these if you're using Google Slides, but you could try to use the drawing tool, I suppose. However, I'm just going to balance them just to practice balancing for fun. So here in front of the KBr, because there's a 2 here, I would put a 2. But then that means I have to change this one also to a 2. That's quick fun remembering how to balance stuff. Let's look at the next one. Aluminum plus chlorine. Aluminum is also a metal. Chlorine is a nonmetal here. They're going to combine. What is the product going to be? Well, let's look up those lovely charges. What is aluminum's charge? +3. Good. It's in group 13. It's under boron, so it goes to +3. What is the charge on the chlorine? Yes, exactly right. This would be -1. So when it forms its product, it's going to have 3 of the chlorines and 1 of the aluminum, because remember the charges have to add up to 0. So this one is going to be AlCl3. That would be the correct product here. Now for balancing, of course, this is a 2 to 3 deal. So we want to put a 2 here, a 3 here, and a 2 here to get that one to balance. You start to see these patterns over and over again. Makes it pretty simple. Now for the last one here, we have sodium plus oxygen. So what do we got for sodium plus oxygen? We have Na and O. What is Na's charge? Group 1, alkali metal, good, +1. What is oxygen going to be? This one's a -2, exactly right. So when they combine, how many of each of the ions do you need? Yes, we're going to need 2 of the Na and 1 of the oxygen. So that's Na2O. Now for balancing here, that means we're going to need, because this is a 2, we need to put a 2 there. And then here we would put a 2 in front of the, no, I'm sorry, that's not a 2, that's got to be a 4. Because 2 times 2, that's 4, so this is a 4 there. If you want to balance and figure out the balancing there. So the basic gist of synthesis is combining the elements together. Okay? And you make sure that you do the charges, and you make sure that you write the ratio so that the charges add up to 0. Gist of synthesis, one of the most basic ones. The next basic one is decomposition, where you're taking the one compound and you're breaking apart into the elements. So single compound breaks down into 2 or more simpler products. We're going to just be breaking down into elements. We're not going to go into anything more complex in terms of decomposition. So starting with the compound, breaking it up into its elements. One of the key factors here, when you're breaking stuff up into elements, is you have to remember your 7 diatomics. You have to remember your Brinkel-Hoff. Okay? Because if you break apart into one of those elements, they have to be written with the 2, or it will not be correct. So let's look here. Cobalt 2 bromide. Okay, cobalt 2 bromide. We're going to break it apart into its elements. So what you should initially write out is just the elements. Like so. Now look at each of those elements. Cobalt, is cobalt diatomic? Is cobalt one of the diatomics? No. Is bromine one of the diatomics? Dr. Brinkelhoff? It is definitely one of the diatomics. So bromine's going to need the 2 here. And if you look at that particular number 1, you'll see that it's already balanced. We don't have to do anything to it. So you get cobalt metal and bromine liquid there. Now for the ammonia, NH3. Ammonia is going to break apart into its elements. Well, let's write those out. N plus H. Then we ask ourselves, is nitrogen diatomic? Is nitrogen diatomic? Yes or no? Some of you at home. Anyone? Is it one of your 7 diatomics? Yes, it is. Good, we needed 2 on the nitrogen. How about the hydrogen? Is it one of your diatomics? Gotta have those diatomics like out in front and center. Or memorize it off the periodic table with the 7 rule. Start at 7, make a 7, and don't forget that hydrogen is the 7th, so this is a yes. That one's definitely diatomic. For balancing here, This is a 3 to 2. So put a 3 there and a 2 there. Last but not least on our decomps, MgO, magnesium oxide, breaking apart. So we get Mg plus O. Is magnesium diatomic? Yes or no? No, magnesium is not diatomic. How about oxygen? Oxygen is diatomic. Very good. Yes, this is an O2. So now, if you wanted to balance, we would put a 2 here and then a 2 there. So decomposition is not that bad. You just have to remember your diatomics. All right, now for combustion reactions. Combustion reactions, remember, we're talking about organic compounds like CH compounds with O2 producing carbon dioxide and water. So this one's actually the easiest of the bunch, in terms of the products at least. Products are always going to be carbon dioxide and water. So basically all you have to do here for this particular one is put CO2 plus H2O. Now we have, we're going to balance this. Just let's review combustion and balancing because it's one of the harder ones. What's the first element that you always balance with combustion? C comes first, so we're going to balance C first. I'm going to put a 3 here to balance my C. What's the second element that we balance? H comes next. Since this is an 8, I'm going to put a 4 here. Then I add up my oxygen on the product side. So I have 3 times 2, so that's 6 in the carbon dioxide, and then I have 4 in the water, because 4 times 1, that's 10. Divide that by 2 because this is O2 over here. That means this is going to be a 5, so you would put a 5 here. And you'd be done with that. That one's easy. All right, looking at the next one, combustion of butane. Not giving you much information there. Does anybody remember what butane is? How many carbons is that? Anybody remember organic prefixes? The first 4 were different. We've already looked at ethane today. That one has 2 carbons. 1 carbon is methane or meth. Does anybody remember the prefix for 3 carbons? It's in our gas grills outside. What gas? Those kind of tanks that you buy for, grilling out. Anybody remember what kind of gas is in there? Yes, it's propane. Very good. So prop is for 3 carbons. So what do you think but is for? How many carbons? Butane is actually lighter fluid. Okay? I don't know if you guys have ever seen lighter fluid if you're lighting charcoal or something like that. But butane is C4H10. Now you could draw this out. We're not going to waste our time doing that, but you put the 4 carbons in a row and you add the H's around, you would know to finish off the 4 bonds around carbon that it would be C4H10. Now, of course, what is the other reactant in combustion? What is it always going to react with when it's combustion? Yes, oxygen. That's the other reactant. And then what are always our products here? Products are always Carbon dioxide and water. Very good. Carbon dioxide and water. Now just for fun, then go back over balancing this one. Start with carbon. So this would be a 4. Then do hydrogen. This is a 10, so we would put a 5 here. Then we would add them up. We would do 4 times 2 in the carbon dioxide. That's 8. 5 times 1 from the water. So that's a total of 13 on my product side. Divide that by 2, that's 6.5. So I could put a 6.5 here. But that doesn't really work because we're going for whole numbers. So in this particular case, then we multiply through by 2. Multiply everything by 2, so this becomes a 2 in front of there. That becomes a 13. This becomes an 8. And that is now a 10. So that one is the more tricky one where you have the odd oxygen. And then you have to multiply through by 2. So very good, very good. Combustion's rather easy because it's always oxygens reacting with, and it's always carbon dioxide and water are the products. Always, always, always. Single replacement, not so easy. Double replacement, not so easy. But we're going to start here at single replacement. And it's been a while since we talked about types of reactions, but a single replacement involves one element, one compound, creating the new compound, and a different element. Element plus a compound gives you a compound plus an element. And they switch. There's a switch that takes place. So one element replaces a second element in a compound. Now that seems pretty easy. However, sometimes elements aren't reactive enough to do the switching. And we have to look at something called the activity series. Do they always occur? No, they don't always occur. And this listing over here, and you can Google plenty of them, but this is called the activity series. Basically showing you the most reactive to the least reactive on the metal list. These ones are the ones that are used most frequently, but you can Google them and find longer lists. Now the activity series isn't anything that you would have to memorize. It will be provided to you on the quiz or in the question, or you can reference it at any point because you would never expect you to have it memorized. There's also, for the halogens, because they do single replacement as well, they follow most reactive is fluorine, least reactive is iodine. So as you go up the group, you get more reactive. Fluorine being the most reactive, iodine being the least reactive. So in order for the single replacement reaction to take place, the element that it wants to join the compound has to be more reactive than the element in the compound already. So as it says right here, the more active element will take the more stable position. It will join the compound. So the more active the element, the more it's going to actually replace. So you look at the activity series, the reactivity chart over there. If you have an element that is lower and less reactive, it is not going to replace one that's higher up. So, same thing for the halogens. Fluorine can replace them all, but chlorine cannot replace fluorine. Neither can bromine or iodine, because fluorine is the most reactive. So, we're going to look at the charts and do some problems here. All right. So the first thing you should do is figure out which ones can switch, because remember, either the cations can switch or the anions can switch. So if we look at number 1, what 2 elements would be doing the switching there? Well, obviously magnesium is the one by itself. So what type is that going to be? Is that going to be a cation or anion replacement? Will the magnesium replace the zinc or will it replace the nitrate? Which is the only one it can replace in terms of possibility? What type of ion is zinc going to be? Is it going to be a cation or anion in that formula? It is a cation. Cations are usually metals or hydrogen. Ammonium sometimes. But nitrate, you know, what's the charge on nitrate? NO3 with what charge? Anybody have the charge for nitrate? It's not -2, but at least you're on the negative side. It is an anion. It is -1. So, nitrate's the anion, the zinc is the cation. The magnesium could only replace the zinc because magnesium's a metal, so it's only going to lose electrons. It's only going to become a cation. Now let's look at our activity series. Here's magnesium. Here's zinc. Is magnesium more reactive than zinc? Is it higher up? Yes, it is. So this one will occur and the reaction will switch. Now you have to think about their charges. Okay, in here, zinc is +2. Magnesium, when it forms a cation, what charge is it going to be? What group is magnesium in? What charge does it form? What group is magnesium in? It's in group 2, so it's going to be a +2 as well. So that's going to be an easy switch. Remember, nitrate's -1, that's why there's 2 out here. So we're going to get the zinc plus the MgNO3 2. Now this one's already balanced because there's 2 nitrates, 1 zinc, and 1 magnesium on each side. So that one's already good. Now let's look at the next one. We have magnesium again, but this time it wants to switch with calcium in there. So let's look at our chart over here. We have magnesium again, but calcium's right there. Is magnesium more reactive than calcium? It is not. So this one is a no reaction. And that's literally what you write here. You put no reaction. It is not going to occur.
So it's only the one by itself that has to be like the most reactive.
The element that's by itself has to be the most reactive in order to switch. Yes. Now let's look at number 3 though, because this one's a little bit different. Number 3 here, we've got bromine. And bromine is a nonmetal. So which one is it going to switch with in there? If it were to switch with it, is it going to switch with the sodium or the chlorine? Which one can it switch with? It can switch with the chlorine. Because nonmetal is going to switch with the nonmetal. The anion would switch with the anion here. Now let's go look at our chart. Here's bromine. Here's chlorine. Is bromine more reactive than chlorine? No, it is not. Very good. So this one is also a no reaction. Remember, we abbreviate reaction RXN. Let's look at the last example here. We have aluminum and copper 2 chloride there. So what is the aluminum going to switch with, the chloride or the copper? Is aluminum a metal or a non-metal? It is a metal, so it should switch with the other metal up there, which happens to be copper. So aluminum should switch with the copper, but let's check. Let's see what's going on here. We have copper, we have aluminum. Let's look over here. Here's copper, and here's aluminum. Is aluminum more reactive than copper? Yes, so this one's going to take place. Now we have to reconfigure our charges. So this is copper 2 chloride. Remember, chlorides are -1. So that means this is a +2 for our copper, because there's 2 chlorides balancing that one out. Copper is a mom, so you have to actually figure out its charge. Aluminum, when it forms a charge, we know it forms a +3 because it's in group 13 under boron. So now the copper is going to just be by itself. That's fine. Copper's not diatomic, so we don't have to worry about that. But when the aluminum combines with the chlorine, where it's +3, the chloride is -2, we're going to get a new ratio for our product. How many aluminums, how many chlorines in that aluminum chloride? 3 of the chlorines to the 1 aluminum. Good, so this would be AlCl3. Now just for fun balancing, remembering 2 to 3. So this is going to need a 2. It's going to need a 3. And this would need a 2. And this would need a 3. So lots of fun there for the single replacements. Those single replacements. So let's talk some double replacement. This is where it really starts to get dicey, a little bit more harder. Double replacement, remember, is the compound plus the compound giving you a new compound and another new compound, where you have the 2 things switching places. The A recombines with the D, the B recombines with the C. So the double switch going on here, or double replacement. Now, they generally take place in aqueous solution and often produce a precipitate, a gas, or a molecular compound. So we got choices here. So I said it's going to get a little bit harder, more challenging for our double replacements. One thing we have to consider is the precipitation aspect. When the 2 solutions of ionic compounds are mixed, a solid may form. Solid may form. That type of reaction, called a precipitation reaction, the solid produced is known as the precipitate. That's when you put like the 2 solutions together and then you see the powdery stuff fall to the bottom. You can predict whether a precipitate will form using a list of solubility rules. Solubility rules. When a combination of ions is described as insoluble, a precipitate forms. That means that it doesn't dissolve in water. So it falls out of the water in the powdery form and drops down to the bottom. So it would be considered to be insoluble. We know things that dissolve in water, we would say, are soluble. Okay? This is where it gets a little complicated. We have solubility rules. Now, like the activity series, you would be provided this chart here. You're not going to be expected to memorize it or anything. But you do have to be able to read it and understand. Now, they have exceptions on here, and it looks a little confusing. So let's read through it. Make sure we know what we're talking about. Soluble ionic compounds. Compounds containing nitrate. So, anything that has nitrate in it, because there's no exceptions to the nitrate. No exceptions. That means if nitrate is in the compound, it is soluble. Period. Acetate. This is the second one right here. Acetate. Also, there are no exceptions. If acetate's in there, it is automatically soluble and it will not precipitate. Now, here comes the ones with the lovely exceptions. Chloride, bromide, and iodide are all the same. If you see those anions, it's silver, mercury, lead. Those are the exceptions. So if you see silver chloride, silver iodide, silver bromide, any of those, are going to form a white powdery substance that falls to the bottom. But everything else with chloride, NaCl, aluminum chloride, any of the other chlorides are going to be considered soluble, no matter what. Sulfate, there's a few extras. Strontium, barium, the mercury, and the lead. Now, mercury is not a big deal because we never work with mercury because it's very toxic. But there are some important exceptions to sulfate. Most sulfates are soluble, but there are some important exceptions there. Those ones fall on the soluble list. Now, all of these other ones down here are considered to be insoluble, or they will precipitate out. Sulfides, carbonates, phosphates, and hydroxides. Now, you can see all their exceptions are pretty much, for the most part, similar. The exceptions here are anything with ammonium. If it has ammonium, it's automatically soluble. If it has an alkali metal in there, so that's going to be lithium, sodium, potassium, rubidium, cesium. If anything has an alkali metal in it, it's automatically soluble. For sulfides, though, calcium, strontium, barium, those are also important exceptions. Carbonates and phosphates are the same. It's just ammonium and alkali metals that make them soluble. Everything else that's with a carbonate or phosphate is going to automatically be insoluble and a powder. The hydroxides are soluble only with ammonia, alkali metals, calcium, strontium, barium. All other cations with hydroxides are automatically going to be insoluble. All right, so can do a few practice before we leave, looking at our solubility rules. Is sodium nitrate soluble in water? Is that a yes or a no? Is it soluble in water? What type of metal is sodium? Sodium's an alkali metal. Guess what? Alkali metals are always exceptions. But also, we have nitrate here. Guess what? Nitrate is always soluble. So sodium nitrate is yes. That one is definitely soluble in water.